Hey there guys. So today we're going to actually start into one of our first real tests. And when we do a statistical test, I want you to think about the fact that what we're actually doing is we're answering a question. And so what is the question we're addressing with this particular test? And by the way, this is a t-test, and it's a t-test, but not in the usual way that perhaps you've been introduced to the t-test in the past. It's even a simpler kind of t-test. Okay, so what is this t-test? What question is it answering? The question that it's answering is, does the mean of a sample that we've drawn, so we've got some parametric population there, we've drawn a sample with a certain n, we've calculated a mean, does y bar calculated for that sample equal some hypothesized mean? So mu is a hypothesized mean. And so we're asking, does a particular mean that we calculated for a group of individuals equal some predetermined value? Now you might say, why would we ask that question? Well, it's actually the beginning of asking about differences, because in this case, the difference, we happen to know the actual parametric mean that's kind of in our mind, and we want to ask whether our sample differs from that. So we're not comparing two samples. Just to be really clear, we're looking at a single sample and asking whether it differs from the mean of some hypothesized mean, okay, which is mu. All right, so let me rephrase this question in a more statistically kind of rigorous way. And this is how I want you to sort of think about things this way as you're doing these kinds of tests. Could a sample with mean y bar have been drawn from a parametric population? You know what that is now, right? It's sort of it's the theoretical population with a mean of mu, a true mean for that parametric population of mu. And so when we rephrase it this way, we can actually kind of think about this problem in a rigorous scientific way. So let's imagine we're plotting possible y bar values, okay? So remember, we could draw samples lots and lots of times. And if we did that, sometimes we would get y bars here, some here, some here, some here, some here, etc. When the true parametric population has a mean of mu, okay? And in fact, we would get a pile of y bars that are in the middle and very close to mu. Okay, let's say mu is right there, the true mean. But we would get variation around that, and it would look like a normal distribution. So we've already kind of covered that idea that we would get a high number of y bars that are near the parametric mean, and fewer the farther away we went. Okay, so that's the first thing I wanted to kind of point out. We kind of already have an understanding of what to expect here. Our y bar is going to be within some limits. I've already talked about confidence limits. And in fact, we want to be able to attach a probability of getting a given y bar. Okay, well that is where we come to the t-test. So just to be really clear here, the null hypothesis is that y bar was drawn from a population whose parametric mean is mu. And the alternative hypothesis, we always want to think about that. The alternative hypothesis to that is that y bar was not drawn from a population whose parametric mean is mu. And we want to attach a probability to the incorrectness of rejecting that. So in other words, our type 1 error probability, or the p-value, which is quantifying that, which is the chance that we are wrong in saying there's a difference, in other words, in accepting the alternative hypothesis and rejecting the null. We want to find that p-value, which tells us what is the chance that we are wrong in rejecting the null and accepting the alternative. Okay, so that is where we're going with this. And I just want to kind of redraw this distribution now. I piled it up with dots, but we have a mu right here in the center, a true population mean, and we are looking at a normally distributed group of y bars around that mean. You recall before we had upper and lower confidence limits on this, so the upper confidence limit on that, on any mean, and this is true of the parametric mean too. If we were to look at the upper confidence limit, we would have mu plus, if we had 0.025, for example, in this tail, and 0.025 in this tail, we would have 1.96 times the standard error. And our lower confidence, so that's the upper confidence limit. And our lower confidence limit would be mu minus 1.96 times the standard error. Okay, and so what is this 1.96? That is in fact the t-value. We derived this before when we were doing confidence limits. And so that is actually giving us a clue about how we're going to do this t-test for any particular y-bar. So for example, let's say we have a distribution, mu, I haven't drawn that very beautifully, it should be nice and symmetrical there, and we get a y-bar of this right here. So what is the probability that we will get that y-bar, right? So how did we compute this t-value, right? How did we compute that particular t? Well, it turns out that that is, we can actually calculate that. So if we were right at the upper limit, we would be saying y bar equals mu plus 1.96 times SE. In other words, at the upper limit, y bar equals mu plus t times SE. And remember, this t is for 0.05 being in both tails of the distribution and an n of infinity in the case of the parametric population. This standard error is calculated from the sample itself because we don't have any other estimate of the standard error, and so we estimate it using our typical, our standard error formula. And so we can actually solve for t here. T equals y bar minus mu over SE, whether or not it's at the upper confidence limit. In other words, it doesn't have to be there. If it happens to be that t is 1.96, it would be right there. Or minus 1.96, it would be right there. But our general formula for t is y bar minus mu over SE. Okay, so for any particular y bar that we get from a sample, we can calculate a t-value, and we can therefore ask whether that t-value, how probable is it to get a t-value that large. Now I want you to note one thing. The t-value could be negative, for example, so this number can be positive or negative. And if our alternative hypothesis is just that they are different, we would want to take the absolute value of this. Okay, and we would look up the significance, the p-value, in a t-table. And you can get those online, or of course they're built into a program like SAS Jump. So we can, for any particular sample, we can ask if it's different from some particular mean. I'm going to give examples in class as to when you might do this kind of thing. We'll calculate it. But what we do is we use a platform and jump test mean equals value. I'll let you try to find that perhaps if you want to look for that. That does this particular test, and it provides an exact p-value, associated with the t that's calculated as the difference between y bar and this hypothesized mean, all divided by SE. Now I can see that some of you might be starting, what is this mu? I mean, why would you ever have a particular mu? Let me give you a real quick example. In population biology, there's this thing called the relative crowding coefficient. You don't need to know anything about it. But if the relative crowding coefficient equals 1, it means that two species are equal in terms of their competitive ability. Okay, so there's a tremendous interest in asking whether RCC is different from 1. So what we do is we hypothesize that RCC equals 1, so that's our hypothesized value. And then for a sample, if we find y bar equals 1.163, it's a very interesting question. Is this significantly different from an RCC of 1? Okay, so that's the kind of situation where you would do this. It also might be that you actually know the mean from other experiments for some infinite group of individuals. All right, now I want to throw at you one more nuance to this, and that is kind of unique to this t-test. Not entirely, but we're going to use it primarily here for this t-test, and that is, so far, remember what we said was our null hypothesis was that y bar equaled mu. And the alternative hypothesis was simply that y bar did not equal mu. Okay? And that will often be the form of our null hypothesis and alternative hypothesis. But there's another way of stating that. We could have the null hypothesis, which will always be y bar equals mu, but the alternative hypothesis could be that y bar is greater than mu. Or it could be that y bar is less than mu. Now, why would we ask that? Well, maybe, for example, our two competing species, one of them is an invasive. And we have reason to believe, due to its size or whatever, that it's going to be more competitive than the native species. And so our null hypothesis would be no difference. Y bar equals mu. But, actually I'm comparing two groups here, aren't I? But I have an index of 1. Yeah, that's right. So, so then my alternative hypothesis would be that the invasive is actually more competitive. So not that it's different, but that it's more competitive. And then I would say RCC, if I formulated RCC that way, that RCC was greater than a hypothesized value of 1. So sometimes you will want to test that what is the probability of getting a y bar in a particular direction from mu? All right, and so if we do that, for example, let's say we want to do a one-tailed test. Really, we're asking then, is y bar in this region, where this is 0.05, and we don't care about this region over here. Okay, that's uninteresting to us because we're asking whether y bar is greater than mu. So we're going to use, if that's the case, a t value that has a different two-tailed probability. And so we're going to have n equals infinity, t equals 2. And it's going to be a much smaller value, right? 6, 4, 5. And therefore, we will actually be much more likely to fall into this range. So that's a one-tailed test, and I'll show you how to do that in SAS Jump as well in class. But you can do a one-tailed test, and by the way, this 0.1 here is the two-tailed value, but half of it is over here and half of it is over here. So you'd use this value to find this particular point. All right, that's it. You know a test, a statistical test, and you can use it. It's a useful one every now and then. All right, bye.